In this video, we're going to address the first two topics in this standard, arc length and area. Linear velocity and angular velocity will be topics we'll get to in the next video. So we're going to look at example 1 that asks us to consider a circle of radius 9 meters or an angle of 4 radians is subtended. Wants us to find the resulting arc length and find the area of the resulting sector. This example should look familiar because we took a look at it in class. Before we get to parts A or B, let's just first note that we can get a good picture for what we're talking about here with 4 radians because we know that right here on the circle is where we get pi radians, and we know that pi is about 3.14. And then down here, we know this is 3 pi over 2 radians, and that's about 4.71. So that tells me, okay, 4 radians. It's a little bit closer to 4.71 than it is 3.14, so I'm going to put it just over halfway between these 2 points on the circle. So that means that this arc that we're being asked about in part A is this arc here, minus kind of my wobbly drawing here. And so that's the arc length we're trying to find. All right, so what did we learn in some of our previous videos about radians, right? Well, we know that if we have an angle in radians, that a formula that goes along with that is arc length divided by radius, okay? And that will always give us the angle in radians. So if you look at what information we have here, we've got the radius and we've got theta in radians, and we want to know s, the arc length. So we can just take this formula that we already know and solve it for the arc length. So this gives us a formula that we actually already knew, but a new way of looking at it, that arc length is the radius times theta, where we make sure that we understand that theta is in radians. So in this case, we know our radius is 9 meters. We know theta is 4 radians, and remember, radians is unitless, so I don't have to put anything here, so I understand when I take 9 meters times 4, the units that I get out for this answer are meters, so the answer here is 36 meters. Alright, so let's take a look at part B. In part B, it asks us to find the area of the resulting sector, so that means we're talking about this area here, and I'll draw a little line there. So we're trying to find the area of that region. So let's understand first of all, let's assume for a second that I actually wanted the area of the entire thing, right? If I wanted the area of the entire thing, I know that I would use the formula pi r squared. That gives me the area of a full circle, okay? But we also understand that we only want a fraction of that area. But if we take a look at what we just did in the previous, in part A, we have this arc length here, right? That doesn't go the whole circumference of the circle. So if we want to understand what fraction of the area we really want, wouldn't it just be this arc length divided by the whole circumference? So if I said S divided by C, then if I multiplied area by S over C, then that should give me the area of the region I'm interested in. Now let's think about what C actually is. C is 2 pi r, and I'm multiplying that by my area, pi r squared. So taking a look at that formula, we can do some simplification. I can see that these pi's cancel out. And I could see that, yeah, I could cancel an r on top and bottom, but here's what I would rather do. Let's look at this right here, s over r. Okay, what is s over r? S over r is theta, right? According to this formula up here that we started with. So I'm going to replace s over r with theta. And then notice I have my little 2 in the denominator here. And so what this formula becomes is 1/2 theta r squared. So for the problem that we're working on here, we have all the information that we need to answer this. So let me step over here for a second. We've got 9 meters as the radius. We have 4 radians as the angle. So we can say area is equal to 1/2 times 4 times 9 squared. And so that gives me an area of 162. And let's understand what our units are here, right? 9, and I forgot to write it in here. That's okay, that's in meters. So I square that. I get, of course, square meters, which we know are the units for area. So here on the next page here is just formalizing both of the things that we came up with on the previous page. Here's a formula for arc length. Here's a formula for area. But here's the big takeaway. For both of these, theta is in radians. Right? So be careful if you're given your angle in degrees. Okay? You can only use the angle in these formulas when it's expressed in radians. So let's take a look at one more example. This one also should look a bit familiar. We have the radius of a wheel is 80 centimeters. If the wheel rotates through an angle of 65 degrees, how many centimeters has the edge of the wheel moved? Or it should say edge of the wheel. I guess it doesn't. My sentence needs a little bit of help here, so we'll add that in there, of the. Okay, so here's my wheel. My imperfect wheel, certainly. And it says it moves through an angle of 65 degrees. So, and we want to know how far the edge of the wheel is moved. Well, to do this, I think it's maybe nice to think of like putting a little dot of paint on the, on really any part of the wheel is fine. Let's go ahead and put it in kind of the standard position here. I'm putting a little dot of paint here. Maybe a little bigger. All right, and so that's standard position, and maybe it'd be useful to think of, the origin being right here. Okay, so here's my dot of paint, and I know about where 65 degrees goes. We've studied where that looks like it goes on the circle. So, 65 degrees might be something like that. So I'm going to put so the idea here is that I'm really wanting to know, when I say how far is the edge of the wheel moved, I want to know this dot of paint, if I rotate through 65 degrees, right, how far did it have to travel to get up here? All right. So we know that this angle, we know the radius of the wheel, and so really this should be a computation of arc length. So we know that this is our formula. S is equal to r times theta. But let's remember the key to this formula. Theta must be in radians. It must be in radians. So what that means is I cannot just blindly go plugging in 80 centimeters and 65 degrees. The thing that goes here must be in radians. So over on the side here, we'll take our 65 degrees, and we know how to convert from degrees to radians. we put pi on top and 180 degrees on bottom, so that way we can see those degrees canceling out with each other. And so you can easily see that you can divide by 5 on both the top and the bottom here. So if I divide by 5 up here, I get 13, and then on the bottom here I get 36. So 65 degrees is going to be equal to 13 pi over 36 radians. All right, so that's what I'll place right here. Now here I could do a little bit of canceling if I like. I mean, we've got really 80 over 1 here, so these are both even. So let's see, I know I can divide 36 by 4 to make 9, and I can divide that by 4 to make 20. And so this could be S is equal to 20 times 13 is 260. Okay. However, I'm definitely not going to leave my answer like this. This is a nice exact answer, but since it's a story problem, I really want my answer to be practical for my reader, and so I'm definitely going to get an approximation here. So typing that in my calculator, I should get 90 point, what was that? I'm going to erase that real quick. 90.8 centimeters. Now, before we just walk away from this problem, let's make sure that that actually makes some sense. So the radius of the wheel is 80 centimeters, right? So right here. So does it make sense that if you rotate through the angle of 65 degrees, that your arc length is actually pretty close to the size of your radius? Well, according to my picture here, that looks pretty accurate. This length doesn't look too far off from this length. So I think that I feel pretty good about my answer here. If there's an error, it's pretty small, or it led me to getting an answer that's pretty close to what I should get anyway. So I think I can feel pretty confident in that.